This is where you accepted the Nobel.
Yes.
Like right here.
Right here.
Tell me about that moment.
Well, it was in the heart of the pandemic, and normally it's done in Stockholm, Sweden. And so the Nobel committee said, well, we're going to send the Nobel to you, and we're going to give it to you in your garden.
When you wake up the next day, does the world just open up, or do you feel a weight of responsibility?
If I'm honest, I mean, it was so overwhelming. I didn't go into science with any thoughts of winning prizes, believe me. I just hoped I could get a job someday. My husband said to me, well, now your main job is being an ambassador for science. And I thought, how do I do that?
Being the face of a scientific revolution is a lot of pressure, even for Jennifer Doudna, a legend in biology who helped turn CRISPR into a breakthrough method for altering DNA, tackling everything from genetic disease to climate change, and spawning dozens of companies in the process. But some critics claim the tech hasn't lived up to its hype just yet, not to mention the ethical concerns. At the same time, movie depictions of biotechnology haven't exactly been great PR for gene editing.
More human than human is our motto.
It didn't matter how much I lied. My real resume was in my cells.
So, to get to the real story, I went to Berkeley, California to meet with Professor Doudna to talk about where CRISPR is actually headed.
I do have a sense that over the next 3 years, we're going to see some continued breakthroughs.
To parse through fact versus fiction in the AI race.
I'm not seeing chatbots in our own experience innovating.
And to gauge how excited or worried we should be.
So do you feel a sense of urgency?
Oh yeah, every day, yeah.
So this is your famous garden.
Well, such as it is, yeah.
How much time do you spend back here?
Not enough is the answer, but I love being in my garden, Emily, because it's a way I refresh my mind. It's amazing how when I come up here and even if I'm just pulling weeds, I feel connected to nature in a way that I find very relaxing.
Doudna's Nobel origin story began in the rainy town of Hilo, Hawaii, where her family moved when she was 7.
What inspired you there when you were growing up?
Well, let's just start with nobody in my family was a scientist. I haven't found a single scientist on either side of my family, but I remember how fascinated I was with just the beauty of the place. And I think that was one of the things that first got me interested in science, was thinking about why, different plants and animals were able to survive there and thrive there.
When she's not untangling life's biggest questions in her backyard, Doudna is teaching, running a lab, mentoring young scientists, and advising startups looking to turn her life's work into real-world cures. Today, she took us inside the Innovative Genomics Institute, a research hub she founded that's part breakthrough lab, part startup incubator.
It's fun, right?
Yeah.
I still kind of get chills when I come in the lab. I love the feel of it. I mean, I still remember my first time going into a research lab and feeling this sense of wonder, kind of the sense of discoveries are being made here and wanting to be part of it.
I can't believe I never realized this, but it was pointed out to me that your name literally spells "do you DNA." I mean, that has to be fate.
It has to be fate, right? I had to work on this.
So what kind of research is happening right now?
Well, we've got all kinds of work going on. We're doing some very fundamental science, trying to figure out the original ancestral origins of CRISPR in bacteria, which is where it comes from. I'm really excited about all the students and postdoctoral trainees that are here that are doing really creative, interesting science. I can't tell you how many times they come up with ideas that I would have never thought of. So recently, a person in my lab figured out that he could extend the efficiency of CRISPR in a whole organism. He's doing experiments in a mouse model of disease by simply accelerating the pace at which CRISPR molecules are able to edit cells.
Wait, let's pause here for a moment. CRISPR. We've been talking about it, but we should probably explain exactly what it is and how it works, right? Okay. The discovery began with Doudna and her collaborator Emmanuel Charpentier and their obsession with the remarkably adaptive immune system inside bacteria. When a virus attacks a bacterium, the defending cell saves a fragment of the viral DNA and turns it into guide RNA, which is like a tiny genetic GPS. If the virus returns, a protein called Cas9, kind of like molecular scissors, pairs with the RNA GPS, then locates and cuts the invading virus. The breakthrough from Doudna and Charpentier was realizing this guide RNA GPS could be reprogrammed, directing Cas9 scissors to cut genomic sequences beyond viral DNA, including human cells. Suddenly, editing DNA was no longer theoretical. And over time, Doudna launched a bevy of biotech companies out of IGI, all working in different ways to translate CRISPR technology into treatments for patients.
Give us a sense of the scope of the number of companies and new ventures that have come out of IGI.
So from the very beginning of the Institute, one of our goals was to ensure that we had a pretty smooth pipeline between fundamental discoveries and the kind of organizations like startup companies that would be able to build real-world value around those discoveries. I think we've now spun out 31 companies at last count, $9 billion valuation if you add it all up. Over 2,500 jobs created, largely here in California, but elsewhere too. It's really extraordinary.
Long before founding IGI, Doudna spent years studying RNA at Harvard and Yale. But it wasn't until 2006 at UC Berkeley that she turned her attention to CRISPR.
Were there nights that you couldn't sleep because you felt you were close to something?
Oh yeah, it had that kind of detective story feel to it. When you're hot on the trail of something, you know that it's very exciting. Can't wait to do the next experiment. CRISPR was very much that way.
What are the current use cases that inspire you the most?
Well, I always think about Victoria Gray, who was the first patient with sickle cell disease to be treated with CRISPR here in the U.S. Her story is so inspiring.
Victoria Gray, an activist and lecturer, is the first person with sickle cell disease to receive an experimental treatment using CRISPR.
I want to reach others who feel like no help is coming. We're coming.
Do you have patients reaching out to you all the time?
All the time.
So you're getting a lot of calls.
We do, yeah. I'll just say that I always thank people for reaching out because they are often sharing very personal stories. A lot of them are about children, their kids. A lot of people will send pictures of their children. It really brings home the importance of what we're doing and, frankly, the need to work as fast as possible on real therapies that can benefit people.
So do you feel a sense of urgency?
Oh, yeah. Every day. Yeah.
Because every day that passes, you could be coming up with a miracle cure or saving someone's child.
Or just realizing that there's still a big divide between the kind of work that goes on in a lab like this, where we're making fundamental discoveries, and actually taking that knowledge and having it benefit people in a real sense. There's a big gap there.
So far, CRISPR therapies, like those for sickle cell, have been built to treat entire groups of patients with the same genetic disease. But in 2025, a new milestone was achieved at the Children's Hospital of Philadelphia when an infant, known as baby KJ, became the first patient to receive a fully personalized CRISPR-based gene therapy.
He was born on Thursday. Friday morning, they had said to me, "Your son is very sick."
In patients who have urea cycle disorders, they can't break down protein. And what happens is ammonia builds up, and ammonia can be toxic to the brain.
We didn't know that we were going to reach his first birthday. Now we're seeing him crawl. Now he's walking. Now he climbs on everything under the sun and thinks he's the most funny person in the room.
Baby KJ's treatment shows a glimpse of what's possible, but the therapy came with a price tag of around $800,000, supported by a patchwork of public research funding, academic collaboration, and philanthropy.
How's baby KJ doing?
My understanding is that he's doing great. He's continuing to grow. He's continuing to benefit from the CRISPR treatment that he received. It's an extraordinary story.
So how do we save more baby KJs?
Right. That's the question, right? It can't be a path that costs millions of dollars. It can't be a path that takes a huge army of people and time to achieve. I'd really like to see a world where we can diagnose people quite quickly who have rare disease, quickly figure out if they might be a good candidate for a genetic therapy like CRISPR. And if the answer is yes, then have a very smooth pipeline for making the CRISPR therapy, testing it quickly, and then getting it into the patient.
One way CRISPR research may accelerate is with artificial intelligence, which could theoretically help scientists design edits faster and predict their risks more accurately. That promise has already piqued the interest of Silicon Valley.
A huge fraction of ChatGPT queries are health related, so we wanted to get really good at this.
One day, maybe we can cure all disease with the help of AI.
It'll look like there's a human professor and 1,000 AI grad students, and they're smarter than you are, by the way.
Doudna is less gung-ho on the matter.
Biology's hard. That's all. I guess it really comes down to that. I've been working in this area for a long time as a biologist. And the more I learn, honestly, the more I'm really humbled by the fact that, biology is complex. We're not going to be able to simulate our way to an understanding of the human body. We're not going to be able to avoid the need for certain types of testing. I do think there are opportunities to increase the efficiency in which we make discoveries about the way our bodies work and the way they interact with drugs that will be effective. And I think AI will be helpful there. But it's going to come down to training models on the right kind of data and a big need for better and more data for training models if we want to achieve that.
An OpenAI executive recently suggested that if a discovery happens on ChatGPT, let's say a drug discovery, that OpenAI should get a cut of sales. What do you think of that?
Good luck.
Expand.
How are chatbots going to change drug discovery? I'm not sure the answer to that yet. I don't know. Lots of people are, of course, very, very hopeful, some very hypeful about it. But I think that innovation is still really in the domain of human beings right now. I'm not seeing chatbots in our own experience innovating. They can be helpful with summarizing data. They can be helpful in writing reports and things of that nature. But I'm not seeing chatbots coming up with a brand new idea for something that nobody else ever thought of.
So you're saying AI can't innovate?
I don't know if it can't innovate. I just don't think it is right now.
What about after the AGI moment?
Well, I never say never, so maybe that'll happen, but I'm not holding my breath.
Well, there are just so many big promises out there, like Larry Ellison saying AI will cure cancer in a 48-hour window. Does that hold any water?
Believe me, I'd be overjoyed if that is true.
We all would.
I don't see it right now.
Doudna's mission is to turn CRISPR from a scientific breakthrough into real-world medicine. But commercializing gene editing means delivering those edits to the right cells safely, reliably, and at scale.
So CRISPR was supposed to usher in this era of miracle cures, and we've seen some. But was the promise overstated, or are we just early?
I think it's a classic example of, this happens a lot in human nature. We get very excited about something, a discovery or a breakthrough of some kind, and you start imagining all the possibilities with it. And then as you start to dig in, you realize that, there's still some challenges. I mean, think about the human genome being sequenced back around the year 2000. Now we're in 2026, so we're 26 years from that moment. And yet, honestly, we still don't understand the function of about 40% of the genes in a typical bacterial cell with a much smaller genome than the human genome. That just gives you a little bit of a sense of the complexity. We recognize that it's a very powerful technology, but it has limitations that have become clear over time.
What are the limitations that still exist?
A lot of it has to do with the way that we put CRISPR molecules into patients. Right now, it's being done mostly by therapies or strategies that involve taking cells out of the patient, editing them in the lab, and then transplanting them back in. And you can imagine that's quite involved, it's quite expensive, it's unpleasant for patients. It's not ideal. So I think going forward, increasingly, there are efforts to turn CRISPR into what we call an in vivo therapy or a therapeutic, where we can deliver it directly into the patient's body in a way that will take these editing molecules to the right cells where they do their job and then don't do anything else.
Is there a time horizon that you like to look at in terms of when, I don't know, there will be some sort of feeling that the sky has been the limit?
It's always hard to put a timeline on things. I do have a sense that over the next 3 years, we're going to see some continued breakthroughs.
2-3 years isn't too far away.
Not too far away.
So what happens in 2-3 years?
For one thing, I hope that we're able to treat more patients like KJ and provide a path for others. We'd like to get more medical centers involved in this type of an approach. We'd like to drive down the cost, of course, partnering with manufacturers that can make the molecules we need more inexpensively, and really just getting more clinical teams involved in this effort. I think if that can be done, then there's really going to be a path to opening the door for many more rare diseases to be treated.
But these large-scale efforts require hefty resources. And over the past year, federal funding cuts under the Trump administration have created significant uncertainty for long-term scientific research. Over the past 3 years, the number of new grants from the NSF dropped 24%. And roughly 25,000 scientists and staff, about 20% of the workforce, have left federal research agencies.
We're a year into the Trump administration. A number of grants have been cut. How does science fare in the age of President Trump?
We're seeing it real challenges right now, as you just mentioned. I think the cuts that we've seen really risk the economic success of the United States in science and technology in a way that is, to me, very unfortunate. We've been a leader in science since the Second World War. On every dollar that's been invested from the NIH in research leads to about $2.50 of economic benefit. That's a pretty darn good return on investment. So giving that up, I think ceding that to other countries, because they will step in. There are opportunities there. If we don't continue our investment in science, others will do so. I think that would really be a shame.
But the Trump administration's impact on science goes way beyond these cuts.
What do you think of the MAHA movement? Is it going to really make Americans healthier or something else?
Look, I think health decisions need to be made based on data and based on science. And there's a reason why people train in medical schools or they go to graduate school to learn about how to evaluate science or to evaluate clinical data or to work with patients. And I think we have to lean into that when we make health decisions.
Mm-hmm. Do you know RFK Jr.?
I don't.
If you had an audience with him, what would you say?
I'd say what I just said to you.
What are your concerns about where this leads? There's the MAHA movement, there's the anti-vax movement. Coming from somebody who worked on RNA, which was a key to the COVID vaccine.
It's a dangerous moment. It's very dangerous. I mean, when I see things like measles outbreak in South Carolina, it's terrible. It doesn't have to be that way.
When you're in a room alone with scientists, what do you privately discuss? Like, what are people saying about this moment?
Well, I think there's a lot of concern. I think that many of us feel, if I'm honest, also a sense of responsibility, that we need to be better at communicating the value of our work, why it's publicly funded, why should taxpayer dollars be used for research, what's the value of what we do. And there's incredible value, but we haven't maybe been very good as a community at communicating that to people that are not scientists.
Does it ever make you want to scream?
Yes. But then, Emily, I look around and I think, I work at an incredible place and I feel also incredibly grateful.
We talked a bit about biotech funding. Researchers say they're considering leaving the United States. What are the implications of this? Does China surge ahead?
I think it maybe does, at least initially. I think that's a possibility. I think it's a very real possibility. Because at the same time that the United States is pulling back on funding, we're seeing a big investment in science in China.
Over the past decade, China's biotech industry has rapidly accelerated, propelled by state-backed investment and a streamlined path for human trials. In 2018, amid this climb, a scientist based in Shenzhen conducted a widely condemned gene editing experiment.
The Chinese researcher has created an international controversy after claiming he helped make the world's first genetically edited babies.
The procedure raised fears of a new era of designer babies, with parents selecting traits for their children, a possibility that remains largely theoretical. Although maybe not for long.
You said we'll see CRISPR-edited babies within 25 years. What kind of edits? And who are these babies?
Those decisions are going to be made by a lot of the people who are coming of age and coming into their reproductive years, I think. Because it'll be a question of assuming that we get to a point where the technology is actually safe and effective for that kind of purpose. Then asking, what kinds of edits should we make? And who should have access to that technology? Who should be paying for that technology? Who should be regulating that technology? Those questions really haven't been answered at this stage.
I know people of reproductive age now and thinking about some of these things. The companies that are promising they can select embryos for traits like intelligence and other things.
It's part of what's been called the Silicon Valley push to breed super babies.
We look at something like height, even eye color, hair color.
Intelligence.
What's actually possible now and what's not possible? Because aren't these traits that are controlled by thousands of genes?
Yes. So I agree. I think it's a tall order to be able to do that kind of selection in an in vitro fertilization clinic. It's also, likewise going to be very hard to know which sets of genes would need to be edited to give you an outcome that affected intelligence or something as complex as that. So I just don't see it anytime soon.
There's this concern, if you select for one trait, let's say intelligence, that you might also end up getting a lot of undesirable traits.
Well, you're touching on something that I think about a lot. All the genes in our cells are interacting with each other in ways that we mostly aren't aware of and don't understand yet. And that means that if we tweak one gene or even a few, we can't always be sure what the outcome is going to be, especially if we're looking long into the future. So I think that's going to continue to be an area where we need to do research. Clearly that work is still at a very early stage. They're working in mice and, they're working in systems that, they haven't gotten to the complexity of a human body yet.
So let's say it becomes increasingly possible. On what grounds can we tell parents you can't do this? Like, why wouldn't you want to engineer babies to be as healthy as possible?
Some people might say, well, I'd like to edit out the sickle cell trait, which, I think one could make a very good argument for wanting to do that. On the other hand, if a parent said, I want to, change something about eye color or height or musculature, some people might feel that it's not appropriate. In the end, I think it's going to come down to probably putting applications of CRISPR into different buckets, where we could imagine one bucket would be for diseases that are devastating, where we have a very well-defined genetic cause and a clear way to make the targeted change in the genome that would prevent that with CRISPR, versus other things that have a lot of risk associated with them, where you might need to be changing many sets of genes that, as you said, would potentially lead to unintended consequences.
You've been called the moral compass of biotech. Does that ever feel more like a burden and less like an honor? And do you ever miss the sort of quiet joy of discovery?
Yes, I miss the quiet joy of discovery. I'd be lying if I didn't admit that. But these are kind of the cards I've been dealt in my career. And so I try to embrace it. I try to learn from it. I try to use it as a way to, to ultimately make sure that CRISPR is going to benefit as many people as possible.
What began with innovation in a lab has grown into an entire CRISPR industry. Startups, pharmaceutical giants, and now AI-driven companies all converging on the next phase in gene editing. But for many, the biggest concern isn't failure, it's success.
Do you ever struggle with unleashing this power on the world, this potential to do so much good, but also it's really scary?
I guess I don't tend to think about it that way. I tend to think about it in terms of the opportunities that CRISPR brings, but I also recognize that there's a responsibility to speak out about the potential risk. At the moment, certainly, I feel very excited about where it's headed. The opportunities to treat people that have rare disease, I think, is here. Potentially opportunities to prevent diseases that affect many of us in the future is coming.
So is it paradise ahead or Gattaca?
Maybe somewhere in the middle, Emily. Hopefully closer to Nirvana.
There's this perception of science as this sort of slow, methodical process. But your journey has had so many dramatic twists and turns. Who plays you in the movie?
I hope it's Kate Winslet.
I like that. I'm a fan. Is there a movie?
I haven't heard of one, but let me know if you hear otherwise.